In this presentation, I'm going to try and clarify a few of the points on pages 21 through to the end of your formulas and amount of substances booklet. There are two percentage calculations that you could be asked to do at AS level. The first one is what's called percentage yield. Now, why have we got a yield? The idea of that is that we're thinking of organic particularly here in this section, but it's in any reaction. What you will find is that you think that you could get a certain amount of product, and when you go through your reactions and you weigh all the products at the end, you find you don't get as much as you think you could. Theoretically, you get, say, 60 grams, you only collect 30 grams of it. So what we have to do is get a measure of how much loss has occurred, and we'll talk a wee bit about why we should have lost in a moment. Now, the equation for it is this. You can see it there at the top of page 21 of your booklet. Percentage yield equals the mass of the product actually obtained divided by the theoretical mass. So you get a fraction of what you got over what you think you should have got, and then to turn it into percentage multiplied by 100. Now, why would you not get 100%? Well, in organic reactions, quite often what you have is transfer from one container to another. So during that transfer, some things stick to the side of the containers, so you don't get as much transferred into the final beaker as you think you should have. There's also what's called side reactions. In organic reactions, you think you're going from one reactant to a product, but actually you can get a side reaction where it turns into a different product. You maybe don't extract it, it's lost whenever you're taking your actual product away, so there's less of your product than you think you should have. And the other one is a topic we'll come on to later on called equilibrium, which means that some of the reactants turn into products, but equally some of the products can break down and go back into reactants again. So instead of getting 100% conversion of reactants into products, it's a smaller percentage. And this is what we're trying to work out. Now, that theoretical yield can sometimes be calculated by our normal mole calculation. So in our mole calculations, when we work this out, so you'll see over the page or a bit further down the page, we're going to do two examples of those. But look at this very simple example. First of all, it says if it was theoretically possible to get 6 grams of ethene, but only 3 was collected, what's the percentage yield? Now, you'll probably straight away instinctively say 50%, and that's correct, because if you look at it, the actual yield was 3, that's what you actually got. What this has told you without doing any calculation is that you should have got 6, so 3 over 6 is a half, multiplied by 100, 50%. If you look at reactions, so on example 2, about halfway down the page, you've got this equation, methane, CH4, reacting with chlorine and turning into dichloromethane and hydrogen chloride. Now, the question says, if 21.3 grams of the dichloromethane, CH2Cl2, were obtained from 8 grams of methane, what's the percentage yield? Now, again, if you look at this, ignore this 21.3 at the moment. That's what we've actually got, but we have to work out, first of all, how much could we've got. So you have to use this, the 8 grams of methane. So let's do our normal mole calculations. So there's our balanced equation to see how they react. 8 grams of methane is going to be 8 over, and then the MR of methane is 16, 12 plus 4, 16. So that's 0.5 mole. Now, theoretically, you should have been able to convert all of that into the product CH2Cl2, so 1-to-1 ratio. So 0.5 mole of methane should have given us 0.5 mole of the dichloromethane. Let's get the mass of that, multiply the 0.5 moles by the MR of this, so 12 and 2, and then 2 times 35.5 is 85, and that gives us 42.5. Now, theoretically, that's how much we should have got. We should have got 42.5. What the question tells us is we only got 21.3. So the percentage yield is therefore the actual yield, that 21.3, divided by the 42.5 and multiplied by 100. And when you put that into the calculator, 50.12%. Now, just before we finish, let's look up at the question. You can see that 21.3 is 3 significant figures. 8.0 is only 2. So it would be appropriate just to give that to 2 significant figures. So 50%, 50.12 would round to 50% to 2 significant figures, and there's our answer. The example underneath it, number 3, is a similar reaction, but there's a little bit different at the end. So 5.6 grams of butane C4H8 is reacted with chlorine to form dichlorobutane. So that's one of our addition reactions from alkenes. And you can see there that we've got a figure for butane. Now what it tells us this time is it gives us the yield. It tells the yield is 75%. What mass of dichlorobutane is obtained? So let's do a normal mole calculation first of all. So butene C4H8 adding on chlorine Cl2 to give us C4H8 Cl2. We've got that number of moles, so 5.6 is our mass, divided by C4H8, 48, and 8 would be 56. So we've got 0.1 mole. Again, we've got a 1-to-1 ratio, so therefore 0.1 mole of the dichlorobutane should have been obtained. And then to get the mass of that, multiply by 127, 4 times 12 plus 8 plus 35.5 times 2, 127. And then if you multiply that by the 0.1 moles, 12.7 grams. So theoretically, we could have got 12.7 grams. Now, what the question tells us is we only got 75% of that. So what we want to do is we want to work out 75% of that. So think of 75% as a fraction, 75 over 100, and then multiply that by the 12.7, and that would give us 9.525 grams. Again, before leaving it, look up at the question. 5.6 is two significant figures, so it would be appropriate to give that to two significant figures. 9.5 would then be our final answer. Okay, over the page, you'll see a number of questions that will give you a chance to practice those. And in a moment, I'm going to flip on a new slide, which will have all the numerical answers. If you want to pause the video now and then try those. There's two sets of calculations. The ones on the left-hand side, questions 1 to 4, are open-ended, so it'll basically work through the whole calculation as we've done. The two on the right-hand side, question 5 and 6, are a bit more structured because sometimes at A level, SIA will ask you to do it step by step. And it's just to give you a practice at doing both types. And what you've got on the next slide is the final numerical answers, so you can check those. If you're happy enough with those, then you've probably done correctly. And at a later stage, probably at the beginning of next week or tomorrow, I'll put up the actual working through on this on another PowerPoint so that you can see step by step if there's anything that you need a wee bit more clarification with. So if you want to try those two page examples, page 22 and 23, pause the video now and then you'll see the numerical answers over the page. So that's the numerical answers to pages 22 and 23. Again, if you want, you can pause and check those. And if you're happy enough with those, then you can proceed to the next pages and do the examples there. Okay. On the next page, page 24, is another percentage calculation. This was called atom economy. Now, the link is obviously the percentage, but it's a slightly different thing, this. Percentage atom economy measures how economical your process is. And if you imagine that you're in a factory and the people are buying in different reactants to turn into a product, what the boss really wants is that nearly all of the stuff that they buy in gets turned into the product. So if you're buying in, for example, 1 ton of one substance and 3 tons of another, and you're only producing maybe half a kilogram of product, there's a big waste there. You've lost a lot of the atoms that you've bought in. So what this is an attempt to do is to measure how efficient is your process in terms of the actual theory behind it. Can you work out the economy? So the idea of it is that you look at the equation. This is all obtained from the actual equation. You look at what you're trying to produce, what we call the desired product, so the substance that you're trying to make by the reaction, and you express it as a percentage of the total mass. Now, usually with most of these, they'll talk about the total mass of product, and that is a wee bit easier to calculate, as you'll see with examples underneath it. And then to turn it into a percentage, multiply by 100. So the example underneath it, look here. So imagine the production of dichloromethane, CH2Cl2, from chlorine and methane. So that's that equation we used previously. Now, what's the percentage atom economy? Well, if you look at the desired product is the CH2Cl2. So if you total up its mass, 85. So that's it. Then the other products you've got are 2 HCl. So to get the total mass of products, take the 85 that you already calculated, and then add on 36.5 would be hydrogen chloride, 35.5 plus 1. And then because we had 2 molecules of that, multiply that by 2. So the total mass of all those substances on the right-hand side of the equation is 158. Now, of the 158, 85 is the desired product. So percentage atom economy is the mass of the desired product, 85 over 158 times 100, and that gives us 53.8%. Now, because these are all based on RAMs to get the mass of the molecules and so on, significant figures probably isn't going to come into it, so we tend to give it to 1 decimal place. So 53.8% there to 1 decimal place, unless in the question they ask you for something different. So read the questions carefully if they come up. Okay, so in the bottom half of the page are two for you to try. So you could pause this and again try it, and then in a moment I'm going to go over these and you can see how you got on with them. Okay, so we'll quickly go over the answers here. So this one is ethane, C2H6 turned into ethene, C2H4, and hydrogen. So the desired product is the ethene, C2H428. The other product is hydrogen, so to get the total mass of the products, 28 plus 2, 30. So the percentage atom economy is going to be 28 over 30 times 100, and that's 93.3%. In the second example, you can see that 2 reactants have turned into 1 product, and you can probably instinctively see that that means that the percentage atom economy has to be 100%. 100% of what was at the start turned into the products. If you want to check it in terms of calculation, the desired product is going to mass of 46. The total products are the same, so they're 46, and 46 over 46 times 100 is 100%. So that gives us the 100% atom economy. Now, on page 25 are 3 more questions that give you a chance to practice those. And again, what I've done on the next slide is I've put the numerical answers up. So if you want to pause this and then try those questions on page 25, and then you can check them against the answers. So there's the answers to the questions on page 25. Apologies, typo at the top, not 23,